having technical issues. Oh, yes.
Okay, so we're starting our discussion here. We're going to get in kind of hot and heavy with acids and bases. And this deals with acids and bases today. And then we'll be getting into acid-base equilibrium as we move through. So some of the equations, and these are equations that actually appear on your equation sheet. pH is going to equal the negative log of your H plus concentration. Remember, H3O plus and H plus are synonymous. Okay, so when you see this, it's the same as this. And I did not do a stellar job of writing that in, but I'm still getting used to this tablet and where everything's writing now that they've rearranged things. Okay, so this is the same thing as this. Got it? Good. So the pH is negative log of your H concentration. pOH is negative log of OH. Your pH plus your pOH equal 14. And that's going to equal your pKw, which we'll get into later. We have another K value here. Our Kw, which is for water, equals the hydrogen concentration and the hydronium hydrogen concentration and your hydroxide concentration. And that all equals 1 times 10 to the negative 14 at 25 degrees Celsius. Remember, your K values are temperature dependent. So if your temperature changes, this Kw value will change as well. All right. So we talked about acids and bases way back in Unit 4. And we talked about the idea between a Bronsted-Lowry base and what that is. That's a substance that's going to donate hydrogen ions in a solution. When the hydrogen ion then interacts with water, it's going to form hydronium or H+. If we're lazy, we just write H+. Bronsted-Lowry bases then accept that hydrogen ion. So when acids and bases are discussed, we oftentimes reference pH because pH is an easier number to work with than some of these concentrations. pH is a way to determine how acidic or basic a substance is. The lower the pH, the more acidic the substance is. The higher the pH, the more basic the substance is. So these are those equations that we can use for that. So pH equals the negative log of the hydrogen concentration. pOH then is kind of similar to pH. pOH then is the negative log of OH. So if we are at 25 degrees Celsius, if our H plus concentration is greater than 1 times 10 to the negative 7th, then our pH is going to be less than 7. Our pOH is going to be less than 7, or greater than, pOH will be greater than 7, and our hydronium or hydroxide concentration is going to be less than 1 times 10 to the negative 7. If all these things are equal, then we're at neutral, and that is where pure water is at 25 degrees Celsius. Bases then are just the opposite. So there's a common misconception that the acid-base scale is from 0 to 14. You can actually have values that are less than 0 and greater than 14. For example, if you had 12 molar hydrochloric, this is actually its pH. It's actually a negative value. So it can happen, but people just, kind of assume that 0 is the bottom. Equilibrium constant then for water can be written as follows. Here is your reaction for that. So your Kw is going to equal H3O plus times your OH concentration. So your Kw for 25 degrees Celsius water is always 1 times 10 to the negative 14. And all of this stuff is written, this is written on your equation sheet for you. So you don't have to have that memorized. So pure water is neutral because the concentration of your hydronium and your hydroxide are equal to one another. We can solve to find the concentration of both hydronium and hydroxide, and then figure out pH as well. So in summary, if you know the pH, you can figure out your H+ concentration and vice versa. If you know your pH, you can figure out your POH, because all you have to do is subtract from 14. If you know your POH, then you can take 10 to the negative POH, and that'll give you your OH concentration. There are other K values for KW, and depending on where you are as far as temperature. So as the temperature changes, degrees Celsius, you can see that the KW and the pH of the water would change also. So if you're talking about sig figs for pH, only the numbers after the decimal point are significant. This is because the value before the decimal point is called the characteristic, and that's described as the order of magnitude of the number. But I would be very, very surprised if they ever had a sig fig question on AP exam that was driven by that. That would be very, very surprising to me. All right. You also need to memorize your strong acids. So I brought no clean clothes is an acronym for that. So this is your sulfate, sulfuric acid, your iodic acid, your bromic acid, your NO3 is nitric acid, your hydrochloric acid, and your chloric acid. That's perchloric acid. So those are your strong acids. You have to memorize those. And then for your bases, all you have to do, you can memorize it if you want. Otherwise, if you just start at the periodic table, okay, it starts at lithium. So it's lithium, sodium, potassium, and then you kick over and grab calcium. And then below calcium is your strontium and your barium. So if you just memorize these, kind of where that break is, that tells you what your strong bases are. And then you just add hydroxide to it. That makes sense? And I guess they're counting cesium in here too. Rubidium? Yeah, I guess rubidium is on there for this one. These are the ones that they typically want you to know for the AP exam, though. So if you just know those 6, I think you'll be okay. But yeah, it's typically your alkali and then a few of your alkaline. All right, everybody cool with that? You got a calculator? You should get a calculator out. All right, we're trying to figure out the molarity. That's the concentration of the H3 plus here. So the way you do that for this is you're going to go 10. Oops, why are you not writing? No. Seriously, come on, just work for me, please. There we go. So in your calculator, you're going to go 10 to the negative 3.689. And the 10 to the, that key is the second, and then your log button. So if you see second and then log, above that it'll say 10 to the X. Do you see that on your calculator? So hit second and then the log button, and then type in negative, not minus, negative 3.689. There's a difference between a minus and a negative, you guys. I think you know that by now. All right, so second log negative 3.689. 0.89. Okay, so your hydronium concentration is going to be 2.04 times 10, or actually a 5. We round. 2.05 times 10 to the negative 4, and that's going to be molar H plus. Now, this is our POH. They want to know the hydronium concentration. So if I do 10 to the negative 6.410, that's going to give me this guy. Okay. Now, I could take him and do 1 times 10 to the negative 14 divided by whatever that value is. Or I think it's faster to take this and subtract from 14. So 14 minus 6.410, that's going to give me my pH then. So my pH then is 14 minus 6.410. That's 7.59. Okay. And now if I take the 10 to the negative 7.59, second log negative, grab that value, bring it down, and I end up with 2.57 times 10 to the minus 8, and that's molar H plus.
So we have to do that for POH every time.
If they're asking for the hydronium, for the H concentration, that's how I do it. Like I said, you can do 10 to the negative 6.41, but that's going to give you your OH. Then you have to take that and do 1 times 10 to the negative 14 divided by that. You should end up with the same answer. But I think it's faster to subtract and get this and then do 10 to the negative this guy, personally. But whatever you guys prefer, you're going to come up with the same answer either way if you do it right.
Wait, what's the way to do it that's not the minus 14?
So why did you subtract that from 14? Because 14 is the highest pH?
No. Well, remember up here we talked, okay? Remember that pH plus POH equals 14. So if you know POH, you can subtract it from 14, and that's going to give you your pH. Okay? Yeah. Now, Jaden, if we have our OH concentration, right, which that last problem, if we have that, okay, that is this guy right here. So if I divide this by my OH concentration, that's going to give me H plus. So 1 times 10 to the minus 14 divided by my OH concentration, that is going to equal my H plus. I just think that it leads you to a lot of sources of error trying to type this guy in. It's a lot easier just to take it and subtract it from 14, personally. All right. So everybody cool with those two problems? Any questions about them? All right. Here we have our OH minus concentration. So what I'm going to do is I'm going to take the negative log of that. So the negative log of 1.56 times 10 to the minus 4. That's going to equal my P. Oh, wait a minute. They don't want to know our pH, do they? Never mind. Let's try this different. Hold on. Let me back up my train. Choo-choo. Back the train up. This is where we're going to do, remember that 1 times 10 to the minus 14 equals OH times my H plus concentration, right? So if I take this and divide by my OH, that's going to get rid of it on that side, and that'll give me my answer. So 1 times 10 to the negative 14 divided by this guy is going to give me my H plus concentration. So 1 negative 14 divided by 1.56 negative 4, and I end up with 6.41 times 10 to the minus 11. Okay. Questions about that?
If we were trying to find the pOH instead of the concentration, how would you find that?
The pOH, so pOH of this would equal the negative log of this value. So if you want to know what that is, negative log 1.56 negative 4. The pOH for this guy would end up being 3.81. And then if you wanted to know the pH of it, you just subtract that from 14. So that'd be 10.2. 10 point, I guess it would be 19 if we want to keep, there we go. Okay. All right, questions? Anything from that, those issues? Okay, so let's look at the next one. The next one, we're dealing with a weak acid here, and they're just calling it HA. They're not giving it a name at all. They're just saying, oh, it's called HA. And they want to know what's happening with this guy. Okay. So if we're looking at the dissociation of this material, we're going to write what's going on with this. So we've got our HA. We're adding it to water. And we're forming H plus, or you can think of it as H3O plus, plus OH minus. So our Ka expression, when this is an acid, our Ka expression then is going to be our products over our reactants, but I'm not going to include water. Why?
It's liquid.
It's a pure liquid. Okay, so that is what my Ka expression looks like. They want us to calculate the H3O plus ion concentration in this. We're given the pH here. So all you have to do is go 10 to the negative 3.456, and that'll give you your H plus concentration. Just as a side note, whatever your pH is here, if you're looking at your hydrogen concentration, that pH is going to be very close to whatever this exponent is here, because that's how pHs and or logs work. Okay. So if we were to have like negative 11 down here or something, that should be a red flag to you that something is wrong. All right, they want us to create or complete the ice table here for this guy. So I'm going to have my I can put my H2O over here if you want, plus my HA yields my H3O plus my OH minus. That water doesn't matter. We're not going to bother with that, so we can just get rid of that part of that column. My HA then, they're telling us that it's starting out at 0.1 molar. And when we start, none of this is broken apart yet. So I've got to lose X here, and I'm going to gain X here, and I'm going to gain X here. Now, we can actually figure out our X value. We've actually done that right here. I guess I can erase these and we can backtrack. I shouldn't have put X in there. I'm sorry. But you know that we're going to gain here 3.50 times 10 to the minus 4. These are in a 1-to-1 ratio, so I would also gain here. And then I'm going to lose that amount over here. So when I am done, this guy ends up being 0.9965. And these amounts are the same. I'm just going to be lazy and not write them in. Okay. So then they wanted us to complete the diagram to find the Ka. We could plug these values in and actually calculate Ka if we wanted to. Okay. And you guys should be familiar with how to do that, right? All right. That is 8.1.
Are we done?
We're done with 8.1. 8.2. Kleenex are back over here if you guys need them.
What did you get on the top?
All right, we've got, we talked about these strong acids and strong bases. When we're dealing with strong acids and strong bases, what that means is the reaction pretty much goes to completion. So your Ka value for these guys are always going to be around 1 or greater because most of it is going to end up being products. For some of these are polyprotic. Some of these are polyprotic acids such as, well, I guess this is the only one. So this guy is a polyprotic acid. So for him, the first hydrogen that comes off is a strong acid. The second one is a weak acid. Strong bases then, strong bases are the ones that are going to disassociate completely in water. So their Kb value, because they have Kb's, the Kb value then is going to be 1 or greater typically. We talked about calculating pH in the last one, how to get from pH to pOH, and that's pretty much all this thing is about, because when we're doing pH or pOH, it completely dissociates, so it we end up with all of it going to completion. All right, so we've got a mixture here. We've got 10 mils. Why are you not moving? There we go. 10 mils of 0.001 molar potassium hydroxide. This is a base. And we got 10 mils of distilled water. So when we do this, we need to first of all figure out what the molarity of this potassium hydroxide is now that it's been dissolved in more water. So we're going to figure out, first of all, what the moles are of this by taking 0.01 liters. This is 0.01 liters here. And we're going to multiply that by the molarity. That's going to give us the moles of KOH. That ends up being 1 times 10 to the minus 5. Then we're going to divide it by the new volume. So 10 plus 10 is 20. So that's 0.02 liters. So that's going to give us a molarity of 5 times 10 to the negative 4. And that's going to be our OH minus concentration, because all of this will disassociate into ions. So you're going to have your hydroxide ions there. And that's what we're looking at. Okay. So this is going to give us the concentration of OH ions. So if I take the negative log of this, so negative log of 5 times 10 to the minus 4, that's going to equal what? What value is that going to give me?
I just can't put on my computer right now.
I don't want a calculation. I want to know what that number represents. The POH, right? That's going to equal our POH. Okay? So the negative log of this is going to equal our POH, which ends up being 3.301. But that's not what they asked for. They asked for pH. So what do I need to
minus 3.
Right. I need 14 minus this value will then give me my pH, which is going to be 10.7. Now, does that make sense since this is a base dissolved in water?
Yes.
Yeah, because this would be a pH greater than 14. That's what a base would be when it's...
This is ruckus.
They're playing a game.
All right. They want to know how we would adjust 100 mils of NaOH with a pH of 12 to get to a pH of 11. So first of all, you need to figure out, are we making it less basic or more basic?
More. Less.
Less. It's going from 12 to 11. So we're making it less basic. So we're going to have fewer OH ions in the pH of 11 than we would in a pH of 12. Okay? So what we're going to do is, if we look, we want to have it at a pH of 11. Right now, it's at a pH of 12. So I want to try to go and figure out what the OH concentration is going to be. So having this in pH form makes it a little icky. Okay? So I'm going to work with POH instead. So what is the POH if the pH is 12? 2. Okay? So we're at a 14 minus 12 is 2. My POH here is going to be 3 because 14 minus 11 is 3. Now, if I take 10 to the minus 2, that's going to give me my OH concentration when the POH is 12 or the pH is 12 or POH is 2. So that
Oh, yeah.
So if I take 0.01, this is going to end up being 0.01 then. So 10, just verify that. 10 to the -2, yep, is 0.01. So that's the molarity of my OH. I need to have my molarity at 10 to the -3 equals OH. I need it here. Okay. Right now, I have 100 mils. So if I multiply this by 0.1 liters, that's going to tell me how many moles of OH I have present. So that's going to end up being 0.001 moles present of OH in there.
How do you know the molarity?
I took, if the molarity, it would be 10 to the -2. Because this is the POH is 2. So 10 to the negative POH gives me my OH concentration. You good now?
Yeah.
Okay. So I need to get my molarity to be this. I know that I have this many moles of OH present, right? Allie, where are you? There you are. You were zoning out somewhere.
I felt like I was in there.
So this is 0.001 moles. I need my molarity to be 0.001. So that means that if I want my molarity of this to be the same value, how much volume do I need?
0.
0.00.
A lot. Wait, what?
Okay. Molarity equals moles over liters, right? I need my molarity to be 0.001 over, this is 0.001. What would X be?
0.
1.
1. 1.
No,
1.
I got it. 1.
You said 0.
Because 0 makes more sense.
X would equal 1 liter. Okay. So right now I have
That makes
100 milliliters. I need to be at a liter. So how much water do I need to add to get that up to a liter? 900 milliliters, right. So I need to add 900 milliliters of water to this solution to be able to change its pH by a factor of 1 of water. Because that would get us to a liter, right? 100 plus 900 is 1,000, which is 1 liter. Okay? All right, homework tonight. Homework tonight, 8-1, 8-2 for tomorrow.
Yeah. We just got back.